we're going to talk about limits and continuity, mostly for two input variable functions. The goals: we want to evaluate a limit when it exists. We want to show when a particular limit does not exist. And we want to show whether or not a given function is continuous. Okay, so hopefully you already looked at the Calculus 1 EpsilonDelta definition. It's just a fancy way of saying for the limit as x approaches a of f of x equals L, the closer x gets to a, the closer f of x gets to L, at least eventually. It's a fancy way of saying that. So what we want to do then in this section is generalize that definition for a function of two input variables, z equals f of x, y. So everything's going to generalize. The notation is going to look very familiar. What this limit notation is saying, as xy gets closer to ab, f of xy is going to get closer and closer to L. It's the same definition. It's just the inputs are a little different. And that's what I tried to say right here. Informally, this notation says that as xy gets closer and closer to ab, f of xy eventually will get closer and closer to L, assuming that limit exists. I can break this down using a diagram that's not in 3D easily enough. So the domain that we're talking about of f of xy, so assuming we have a function z equals f of xy, the input values are points, right? The input values are points, which means the domain of f is a subset of the xy plane, which I've pictured here. This is, the xy plane is what we've called in the past R2, right? We've used that notation in the past. D is a subset of R2. So what this blob represents, D represents the domain of f of xy and its surrounding points in R2. In other words, D is a subset of R2. So what that definition is saying is this: if you take a point, let's call this point AB, if z equals f of xy, and if this is true, that the limit as xy approaches ab of f of xy, if this in fact does equal L, then the epsilon delta definition is simply saying this: if you take an epsilon bigger than 0, so let's say this distance between L and whatever this upper interval value is, we're thinking of this as a z-axis, I suppose, but it's a number line. Let's say that distance is epsilon. Then this value would be L plus epsilon on this number line. And down here, you could think of this value right here as being L minus epsilon. So if this definition is true, then for any epsilon greater than 0, I should be able to choose a delta greater than 0. So delta is a distance value. So let's suppose we have a disk around AB and that the radius of this disk is delta. What the epsilon delta definition says is, hey, for any epsilon, you choose it. You choose your epsilon greater than 0. If this limit exists, the idea is you make it as small as you want. I can find a delta such that as long as I pick a point xy within delta units of AB, the thing that xy is approaching, right, in the limit notation, as long as I pick an xy inside that little disk that has center AB, then f of xy will be inside that epsilon interval. That's what has to occur if this is in fact true, if the limit of f of xy as xy approaches ab equals L. But again, don't get lost in all that. All it's saying is this: if this point that I picked is close enough to AB, then f of xy is going to be close enough, as close as we want to L. In other words, as xy gets closer and closer to AB, f of xy gets closer and closer to L. It's the same, basically the same definition from Calculus 1. So here's the definition. Let f of xy have domain values arbitrarily close to AB. So it's very important that xy can approach AB and get as close as we like, okay? The limit of f of xy as xy approaches AB equals L if for all epsilon greater than 0. It means you choose the epsilon. It doesn't matter how small it is. For all epsilon greater than 0, there exists a delta. That means given an epsilon, you can come up with a delta greater than 0, such that this notation, saying the absolute value of f of x minus L is less than epsilon, is a fancy way of saying the distance. Remember, absolute value measures distance, right? This is a fancy way of saying that the distance between f of xy and L is less than epsilon whenever, okay, think about what distance is in the xy plane. This is the distance formula in the xy plane. Whenever the distance between xy and AB is less than delta but bigger than 0. In other words, xy is not going to actually be A and B. So once again, this is just a fancy way of saying, hey, you pick x and y close enough to AB, the distance between f of xy and the limit value is going to be less than whatever you like, epsilon, whatever you like. The closer xy gets to AB, the closer f of xy gets to L. So some notes on the epsilon delta definition of limit. Note number 1. The epsilon delta definition says nothing about the value of f of AB, or if it even exists. In other words, we don't care if L equals f of AB. It does turn out to be true when the function's continuous, that turns out to be the case, but it doesn't have to, okay? It's just, remember what the notation says. xy is approaching AB, but we never think of it, when we're talking about a limit, we never think of it actually as getting there, right? At least intuitively, that's what we think of. It's approaching AB, but xy is never actually getting there. Note number 2, xy can approach AB from any direction in the plane. For the limit L of f of xy to exist, L must be the same no matter which path xy takes to AB. When you look at the Calculus 3 picture, xy, well, that can approach AB from any direction. It can approach from this direction, from this direction, from this direction. And from every single direction, you have to get the same value of the limit for the limit to exist. So note number 2 goes right into note number 3. To prove that a limit doesn't exist, you can find 2 paths to AB that give different limit values. Remember, think back to Calculus 1. If the left-hand limit didn't match the right-hand limit, so the notation you used was the limit as x approaches A, superscript positive, right? So the left-hand limit looked like this. The limit, this would be the right-hand limit. Remember that? A positive, from the positive direction. And then this would be the left-hand limit. X approaches A from the negative direction. And in order for that limit to exist, then these guys had to be equal, right? They had to have the same limiting values. So if they weren't equal, then the limit didn't exist, did it? Well, we can say the same thing here. If you can find 2 paths, it doesn't matter which 2 paths, where the limit on one path doesn't equal the limit on the other path, then the limit doesn't exist. So it's very important you realize note number 3 cannot be used to prove that a limit does exist. You can only use it to show a limit doesn't exist. Very important you realize that. Because if you wanted to use this idea to show that a limit does exist, you'd have to show that the different limits, or the limits on different paths are the same for every path, which is impossible to show that a limit exists that way because there's an infinite number of paths you can take to to AB. Think about it. If this is a point, AB, in some subset of the xy plane, D for domain, then there's an infinite. I could draw straight lines. I could take straight line paths. So imagine xy on this straight line path. I could take a parabolic path, maybe looks like that, to AB. I could take some weird wiggly path. And there's an infinite number of ways you can draw this, an infinite number of paths you can take. So there's no way you can use note number 3 to show that a limit does exist, only to show that it doesn't. Okay, find the limit if it exists. The limit as xy approaches 0, 0 of 2xy divided by 2x squared plus y squared. So the function f of xy, this is f of xy. And you might think, well, the limit doesn't exist. You might think that automatically because when you plug in x equals 0 and y equals 0, you get a denominator of 0, right? But you also get a numerator of 0, don't you? Well, no, don't think L'Hopital's rule in this class for two variable functions. We're not going to try to use that. There's a problem with that. Which derivative do we take with respect to x or y? So L'Hopital's rule is out the window for this type of limit. So how do we show it doesn't exist or it does exist? One thing you can do to get a feel for whether or not it exists is you can look at a table. I'm going to show you on Excel how to create a table of values when you have two inputs. To create a table with two inputs, what you do, one way to do it in Excel is, and don't ask me why this works, I don't know why, I just know how to do it. You can make your input in that cell in the upper left-hand corner 1, and then the next cell down, make that 1. And then in the next cell down, input the formula. So I don't know if you've ever played with Excel, but to input a formula, you have to put in equals first, and then it knows that you're inputting a formula. And what we want to do is input this formula. X1, we're going to call this cell right here, this first cell is called A1. So we're going to call that A1. And then we actually need to multiply by 2, right? So 2 times A1, and then times A2. That's the numerator. So I'm calling A1x, A2y, and then the denominator as well. So I need to divide by a quantity, so I have to put in parentheses here. Okay, 2x squared. Well, that's 2 times A1 squared. So that's the caret shift 6, 2. So it's like calculator notation there. And then plus y squared. So plus y squared. Sorry, that would be A2 squared. Sorry about that. A2 squared. Okay, so that looks right to me. Okay, so, and we get a value there, but don't even worry about what that says right now. I mean, it's plugging in 1 for x and y, so you get 0.666 blah. It's 2/3 basically. So what we want to do is analyze what's happening as both x and y, A1 and A2. Well, it's not really A1 and A2. You'll see. We want to see what's happening as x and y approach 0. 0 both ways for x and for y. So here's what we can do. Let's start at, say, negative 0.2. So these are going to be x values. And let's go by maybe, I don't know, 0.05. So the next one would be negative 0.015 or 0.15 rather. There we go. Okay, now what you can do to extend this pattern out is, do you guys know about this? Drag this corner down. So there's negative 0.1, negative 0.05, 0, and then I'll go all the way to 0.2. There we go. So those are going to be my x value inputs in the table, okay? And then I want to put the same inputs across the top. Now let me I don't need any space there. Okay, so I want to put the same values across the top. So we'll start at negative 0.2 again. I probably could copy and paste, but I'm not going to. Negative 0.15. And then let's drag the lower right-hand corner. Negative 0.050, 0.051, 0.2. Oops, didn't get quite far enough. There we go. So these guys will be my y values. These guys will be my x values. So how do you get it to fill in the table? Well, you're going to highlight everything, including that first output value down there. And then go to data analysis. Let's see. Go to data. And then the what if analysis will do it. Data table. It seems like a lot, but you do it a couple times and then it's not a big deal. So this is the part that I always forget. So what you want to do is you double check it to make sure that you didn't switch the x and y's around. So you want the row input data to either be A1 or A2. Let's just try it one way, and if it doesn't work, we switch it around. And then make this A2, hit OK. And it fills in your table for you. So what if analysis, data, A2, A1, okay. 0, 4, there we go. And then it exactly matches that. You see that? So that's kind of your test. So if you want to remember it, it's A2 first when you do it this way, and then A1. But that should work. So look at what's happening. So remember, these guys over here are x values. So as x approaches 0 from the left or from the right, that would be from the left would be going down towards 0. From the right would be going up towards 0, positive values towards 0. And then across the top, you can see that y is approaching 0 from the left and from the right. So what's happening as to these function values in here as both x and y are approaching 0 here and here? Well, one thing I notice about this table is as you look at x values and y values that are equal, negative 0.2, negative 0.2, negative 0.5, negative 0.5, it looks like we get the same value every time. What does it look like we get? It looks like we get about 2/3. However, so that would be one path that you could approach 0, 0 by. It sure looks like if x equals y, we get about 2/3 as the limiting value, doesn't it? However, if, say, you approach on the path where x equals 0, sure looks like the function values are 0, right? That would be the limit value. The function values are 0 if x equals 0. If we approach on a path where x equals 0. X equals 0, that would be on a path on the y-axis, right? Likewise, if we approached on a path on the x-axis when y is equal to 0, sure looks like we get a function value of 0. So it looks like on at least 2 or 3 different paths, we get different limit values, don't we? Back to this problem then. Remember what we were supposed to do. We want to find the limit if it exists. Well, I don't think it exists, do you? So what we could do is look at 2 different paths and show that we get 2 different limit values to show that the limit does not exist. That's the upshot of all this discussion. The path y equals x is one path to take. And I'm pretty sure I should get, based on the table, I'm pretty sure I should get 2/3 here, right? So what do I mean by taking a path y equals x? Well, what I mean is, if you think about the function notation, what I mean is, okay, this is kind of the generic function notation. The limit as xy approaches 0, 0 of f of xy. That's the generic notation. Let's adjust it for what we're doing here. We're going to take the limit as, Okay, what are we going to replace y with? X. Or I suppose we could replace x with y. But we'll replace y with x. So we're going to take the limit as x is, you know, on the line y equals x is what this is saying. The path is y equals x. So on that path to 0, 0, we're taking the limit of f of x, y. But wait, what's f of x, y? F of x, y is this thing, so why not just put that in there? 2xy divided by 2x squared plus y squared. Now, the thing is, I can replace y with x in that formula. And so this guy becomes the limit as xx approaches 0, 0. Think about it. If I replace this y with x and this y with x, I get, what do I get on top, you guys? 2x squared, and what do I get on the bottom? I get 2x squared plus x squared, which is 3x squared, and what's going to happen? These guys cancel, and I get 2/3. You know, and this is assuming that x and y never both get to 0. So xy does not equal 0, 0. In other words, x and y at the same time don't equal 0, 0. So on that path, y equals x, the limit is 2/3. Does that make sense to you? Now let's take either a y-axis path or an x-axis path. It doesn't matter. So what do you want the next path to be?
Can't you just say y equals x squared?
You could.
Plug in a different value. Right?
You could, and you might need to do that in the homework, yeah. But how about, I think it'll be even easier if we let y equals 0, right? So if we let y, in other words, we approach 0. When is y equal to 0? On the x-axis, right? So we're going to, xy is going to approach 0, 0 on the x-axis. That's the path we're taking. That's what it means when you say y equals 0. So in this situation then, you could say that the limit, okay, I'm going to go ahead and plug it in right away. I'm replacing y with 0 as x0 approaches 0, 0 of f of xy. Well, that is 2x. Okay, so if y is 0, couldn't I replace in 2xy, couldn't I replace y with 0? So 2x times 0, 2xy is 2x times 0, divided by 2x squared plus 0 squared, right? And what does this turn out to be, by the way? Well, yeah, you get 0 on top, right? So 0 over, by the way, I'll keep the limit notation. So same limit notation. But this guy becomes just 0 over 2x squared. Remember, we're not letting x get to 0, otherwise you'd have division by 0. But that's what it becomes. 2x times 0 on top is just 0. And that's just, that whole thing is just 0 then, right? Along that entire path, along the entire x-axis then, the thing we're taking the limit of, f of xy, is 0. So what's the limit of 0? No matter what xy is approaching, but in this case, the limit of 0 as xy approaches 0, 0, the limit of a constant should be a constant, right? So on one path, here's the point of all this discussion. On one path, we got a limit value of 2/3. On another path, we got 0. This limit does not exist. You could make a note of the fact 2/3 does not equal 0, so the limit doesn't exist. Okay, we're not going to focus on epsilon-delta proofs, so breathe a sigh of relief. But I'm going to show you a very basic epsilon-delta proof. And there's a reason. It's kind of almost so easy it's silly, but there's a reason I'm showing it to you, because it's going to allow us to build up some ideas. This proof will give you an idea of how epsilon-delta proofs are done if you haven't seen that before or you don't remember it. But again, it's not going to be there's going to be one example of this in the homework, or one homework problem that looks just like this one, except it's an x instead of a y there. So you can model your work on this problem. Okay, so in this example, you guys, we're going to prove that the limit as xy approaches ab of the function f of xy, which is just y, equals b. So very important you understand this y is our function. F of xy is equal to y here. So we want to show that the limit as xy approaches ab of y is just b. And notice what we're doing then, by the way. It looks like we're just plugging in this b value for y, which is what we call that direct substitution, if you remember that from Calc 1. So how are we going to do that? Well, we're going to use the epsilon delta definition. So let's write it down. The epsilon delta definition, anytime you prove something using the epsilon delta definition, it's not a bad idea to write it down to remind yourself of what it says. So the epsilon delta definition says that the limit as xy approaches ab of f of xy equals L if, I'm going to show you some more advanced mathematical symbols so that when you see it on Big Bang Theory, you'll know what it means. When you see this upside down capital A, has anybody ever seen that before? It means for all, okay? I don't know why it means for all, but it does. If for all epsilon greater than 0, have you seen the backwards E before?
Yeah, there is.
Yeah, there exists. There exists a delta greater than 0, ST, such that the distance between f of xy and L, that's just using absolute values, you could just subtract L from f of xy inside absolute value. That means distance between f and L. So this thing equals L if for all epsilon greater than 0, there exists a delta greater than 0 such that the distance between f and L is less than epsilon whenever the distance between xy and AB is less than delta, but bigger than 0. In other words, xy doesn't equal AB. So how would you say that? Oh, you just use the distance formula. The distance formula for the distance between xy and AB, okay, that's x minus a quantity squared underneath the radical plus y minus b quantity squared. We want that to be less than delta, but bigger than 0. So this is the definition you want to, if you're ever asked to do an epsilon delta proof, if you take more advanced math classes, you will see a lot of these. This is the definition you want to keep in mind. This is not part of the proof, by the way. It's just the definition you use to prove what you're asked to prove in the example. So what we need to do to prove that this limit is b is we need to somehow relate this distance and this distance. We need to somehow relate these to each other. So I want to say this. Note that the square root of x minus a quantity squared plus y minus b quantity squared, would you believe that this is going to be greater than the square root of y minus b quantity squared? Would you? I suppose it could be greater than or equal to if you make a equal to x, but y not equal to b. I suppose that could be an or equal to statement. Would you believe that statement? Why does that have to be true?
The radicand on the left is going to be greater than the radicand on the right.
Exactly. This is a positive number, and you're taking it away, right, from the radicand. So this guy on the left has to be bigger than the radical on the left has to be bigger than the radical on the right. But here's the thing, you guys. This radical right here is the absolute value of y minus b. When you take the square root of something squared and you don't know if the thing that's being squared is positive or negative, you need to put absolute values around it when you take the square root of the guy being squared. But here's the thing. We've made the connection now between the distance between xy and AB and the distance between the function value and L, because guess what? Y This y value, remember, is our function. And this guy right here is our L. So f of xy minus L, oh, we've made our connection, haven't we? Between this guy, in the statement it's that guy, and this guy, in the statement it's, of the definition, it's that guy. Okay, so now here's what you can do to finish the proof. You always want to say, really, we haven't even started the proof yet. You always want to say, let epsilon be greater than 0. So it's anything you want it to be in the universe. It's just got to be, we usually think of it as some little number bigger than 0. Let epsilon be greater than 0. Then choose, it's going to turn out that if you choose delta to equal epsilon, it should work out fine here. Choose delta to equal epsilon. Note that whenever the square root of x minus a quantity squared plus y minus b quantity squared is less than delta, but bigger than 0. Note that whenever this is true, the absolute value of y minus b is also less than delta. Right? Didn't we establish that up here? But delta is equal to epsilon. So this completes the proof. This does it. Again, if you haven't looked at the definition a long time, this is probably all Greek to you, and that's okay. But all I'm saying is, if we assume this is true, that's what I mean by the whenever. If we assume this is true, since this guy is less than this guy is also less than delta, right? And since we assume that delta, we can choose delta to be anything we want, since we assumed that delta equals epsilon, we've just shown what we were required to show, that we can get the distance between f of xy, which is y, and L, which is b, to be less than epsilon for that choice of delta equaling epsilon. That's it. It's almost automatic. But there's a reason why we're showing you this one and only epsilon delta proof. It's going to allow us to make a number of conclusions. So more notes on limits. First of all, the proof that the limit as xy approaches ab of x equals a, that's going to be the homework problem, is similar to the last example and is going to be left to you guys. Number 2, it is still true that the limit as xy approaches ab equals a constant, or no, I'm sorry, the limit as xy approaches ab of a constant is equal to that constant. I'm not going to prove that, but it wouldn't be hard to do. The limit laws, do you remember what the limit laws say? I'll write one of them down for you. The limit, so this is a calculus 1 limit law. The limit as x approaches a of f of x plus g of x, what does that equal? So you're taking the limit of a sum of two functions. What does that equal to? Well, you're thinking of a derivative, but a derivative has the same property. In other words, you can split up the addition, right? So, or you can split up the limits over addition. So the limit the limit of a sum is the sum of the limits. I like saying it that way, right? So symbolically, that's when we say the limit of a sum is the sum of the limits. That's one of the limit laws. By the way, does it work just as well for subtraction? You bet. So there's 2 of the limit laws right there. So note number 3 is talking about those limit laws that you learned about in Calculus 1. The limit laws hold for multivariable functions, i.e. the limit of a sum or a product is the sum or product of the limits. The limit of a constant times a function is that constant times the limit of the function, in other words, you can pull the constant out front, etc. The proofs of these laws are similar to the ones for single variable functions. If you had a rigorous math teacher, then you might have done some of those in Calculus 1. Using the epsilon-delta definition, you might have proved some of those limit laws. I'll just assume you did. Do you remember the squeeze theorem? The squeeze theorem holds for multivariable functions. I will show you an example of that in just a little while. The squeeze theorem holds for multivariable functions. Here's the quick version of the squeeze theorem. Let's say you have a function f of xy. And let's say you have a function g of xy. And let's say you have another function. What's a good name for another function? H of xy. Let's say h of xy is always between, at best equal to, f of f and g. Then if, what the squeeze theorem, this is very informal, but it's a nice way to think about it. If the limit, remember the arrow notation for limits? So if the limit of f of xy as xy approaches some ab equals L, and the limit as xy approaches the same ab, it has to be, of g of xy approaches L, then guess what the guy in between squeezes to as xy approaches ab? It also has to approach L. That's the quick version. I mean, it's not very formal. I'm not using the notation that I'm supposed to use, but I think it conveys the idea of what the squeeze theorem is.